All right, now today we're going into chapter 6, 6-2, and 6-3. So by the end of today, you will be able to turn in your chapter 6 notes, okay? All right, and chapter 6-2 is classification of elements, and chapter 6-3 is periodic trends. Chapter 6-2 is very, very short, very short. I already taught most of it to you guys. So chapter 6-2 should be pretty easy, not much notes there, okay? So here's our first video. This is a very, very good video. I do recommend you guys watch this again, okay? So pay attention to this video. It explains a lot. Oops, let's go back.
Hey, it's Professor Dave. Let's talk about the periodic table.
He knows a lot about the science stuff. Professor Dave explains.
Pretty much everyone knows what this is, even if they don't know much about chemistry. It's the periodic table of the elements, which at first seems like a random arrangement of substances, most of which sound strange and foreign. But the way the elements are arranged reveals many beautiful patterns that tell us about how nature operates. In the mid-1800s, lots of chemists were trying to come up with a way to depict all the elements in table form, and many different formats were proposed. But it was the one by Dmitry Mendeleev that stuck, because of how well it correlates data as well as its predictive powers. He arranged the elements into rows called periods and columns called groups. Elements that had similar behavior were put in groups together, which helped to correlate existing data. And it also predicted the existence of elements that had never been seen before. With the gaps in the table, Mendeleev said there must be elements that go in these spots, and he predicted some of their properties. Eventually, these elements were discovered with the properties precisely as expected, and now we have all the metals, metalloids, and non-metals organized nicely. It wasn't known at the time, but the reason elements in the same group behave similarly is because they have the same number of valence electrons. Look at group 1, for example. These elements all have one valence electron, or one electron in their outermost shell. As you go down the table and n increases, you gain a shell each time, but whichever is the outermost shell, there is only one electron in it. Every element in group 2 has 2 electrons in its outermost shell, and so forth. This simple fact determines many characteristics about each element in ways we will continue to see as we learn more chemistry. There are some periodic trends that we can recognize when we look at the table. The first one is atomic radius, or the size of the atom. As we proceed downwards on the table, atomic size increases because we add shells. As we go to the right, atomic radius decreases because we are moving within a shell, and each element to the right has one more proton in the nucleus than the last. So there is a stronger electromagnetic attraction felt by the electrons, and the radius shrinks. That means overall, atomic radius increases going this way on the periodic table. Ionic radius is a little different. Electrons repel each other, so adding an electron makes an atom bigger. Taking one away makes it smaller. Ions with the same electron configuration will have their radii decrease as the atomic number increases. Next, we look at ionization energy. This is the energy required to remove an electron from the atom. It will always be an electron in the outermost shell. The electromagnetic force that attracts the electrons to the protons drops off very quickly with distance. So the farther away an electron is from the nucleus, the easier it is to pull it away. This means the ionization energy trend is precisely the opposite of the atomic radius trend. Francium, a very large atom with only one valence electron, will be easy to ionize because the electron is so far away from the nucleus. And atoms like to have their outermost shell completely full. Losing the electron means this shell is gone, and the one below is completely full, so elements in group 1 will easily lose one electron. Looking at the opposite corner with helium, there is only one shell, so the electrons are very close to the nucleus, and the shell is full, so it is very stable. For this reason, it requires much more energy to ionize helium. So the ionization energy increases going this way on the periodic table. Elements can have successive ionization energies for removing more than one electron. A second ionization energy will always be greater than the first and continue to increase from there, since the more electrons you remove, the less stable the atom becomes. An element will have a huge jump in ionization energy after you take the last one in a shell, because then you jump to the noble gas electron configuration from the previous shell, which is full, so it really won't want to give up any more electrons. There are just a couple exceptions to the ionization energy trend, but we can rationalize them. Look, for example, at the second row. From lithium to neon, the ionization energy should increase each time we add a proton to the nucleus and the radius contracts a little. But something like oxygen, which dips downwards from nitrogen's ionization energy, does so because of orbital symmetry. Here is nitrogen's orbital diagram, as well as oxygen's. Notice that nitrogen's 2p orbitals are precisely half full. This gives nitrogen a special stability, just like elements that have a full outermost shell. If nitrogen loses an electron, it loses that special stability. But if oxygen loses an electron, it will gain that special stability. That's why oxygen's ionization energy is a little bit lower than nitrogen's, even though oxygen has one additional proton. All deviations from the ionization energy trend can be explained by discrepancies in orbital symmetry, like this one. Next, we will look at electron affinity. This is exactly the opposite of ionization energy, since ionization energy is how much energy you need to remove an electron, and electron affinity tells us how much an atom wants to gain an electron. Disregarding the noble gases, as their shells are full, electron affinity increases this way. Fluorine has the highest electron affinity because if it gains one electron, it will have a full shell, or a noble gas electron configuration. Looking at the opposite corner, these elements don't want to gain electrons. They would rather lose them. Exceptions to this trend happen for exactly the same reasons as the exceptions to the ionization energy trend. Lastly, we want to look at electronegativity. This is the ability of an atom to hold electrons tightly. It will increase this way because a smaller atom like fluorine with more protons for its energy level, or a higher effective nuclear charge, will hold electrons best. Again, we will disregard the noble gases for this trend. Electronegativity will be important in the next clip where we learn about chemical bonds. So the trends to remember are atomic radius, which goes this way, as well as ionization energy, electron affinity, and electronegativity, which all go this way. Let's check comprehension.
Okay, so again, I recommend you guys watch that again. It's a very good, comprehensive video. Okay, so I am going to go over some of this stuff in a little bit more detail. Organizing the elements by electron configuration. So if you take a look at the periodic table and its electron configuration, this whole first column is an S. It's an S1, okay? So 1s1, 2s1, 3s1, this whole column is an S1, which means it has one valence electron. This whole column has two valence electrons, S2, 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 S2. This column over here, it looks like it has one valence electron, but remember there's 2s2 and then 2p1, so that's 3 valence electrons. 4, 5, 6, 7, and 8 valence electrons. Okay. All right, so let's take a look at the valence electrons. There you go. Now, notice the one exception to that rule. So we have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Look at this exception right here. There are only 2 electrons in the valence here. Okay. All right. Now, let's talk about the atomic radius. How can you memorize the trend? Okay. How can you memorize the trend? Well, from left to right on the periodic table, from left to right, it increases in atomic number, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? From left to right, it increases in atomic number. That means that your number of protons also increase. Okay, number of protons increase. Make sure your mic's off, John. So your number of protons increase, which means it makes it more positive. Okay. If it's more positive, then it's going to suck in the electrons more. it's going to hold it tighter, which means it's going to get smaller, okay? So let's take a look at that. Increases the number of protons, more positive, attracts the negative, makes the atom smaller. From top to bottom, we're adding, think of it as adding layers of clothes, okay? So when you add layers of clothes, like, you know, I don't know if you've ever seen those kind of commercials where the little kid is going out into the snow and the mom puts on layers and layers and layers of clothes. And so later on, the kid is like this and can't move because it has so many layers of clothes. So it's that type of idea, okay? In period 1, you have 1 layer of clothing, okay? It's just a t-shirt. On period 2, you're going to have a long sleeve shirt on top of that. On period 3, you're going to have, you know, a light sweater on top of that, you know, and so on and so forth. So you're adding layers. And so because of that, because you're adding shells, energy shells, you're going to get bigger and bigger, okay? So as you go down, you get bigger and bigger, all right? All right, so now here is a visual on what the atoms look like. So as you move down the periodic table, you get bigger and bigger. As you move to the right, it gets smaller and smaller. Again, why does it get smaller? Because it gets more positive. More positive means it pulls the electrons in more. And if it pulls the electrons in more, then it gets smaller. Okay, so generally decreases as you go to the right, generally increases as you go down. Okay. Now let's talk about ions. What happens with atomic size with ions? When you lose an electron, let's kind of think about what's happening here. When you lose an electron, okay, it becomes more positive. If you lose an electron, you become more positive. If you become more positive, then you're sucking in the remaining electrons more. You're pulling them in closer, okay? And then that makes the atom smaller. Now you could use an analogy for this one. You can imagine a little kid. Let's say you have a 2 or 3 year old. Okay, some of you guys even have little brothers or sisters who are 2 or 3. And imagine they have a whole mess of toys around them. Okay, they have a lot of toys around them. It's a mess. And then another kid comes in and takes one of the toys. Then your little brother or sister who's sitting there with all these toys are all of a sudden going to do what? They're going to suck in their toys closer to them so that the other kid can't take any more toys. It's the same idea, okay? So when one electron gets taken away, all the electrons come closer and closer to the atom, the nucleus, okay? All right, now losing an electron may also get rid of one of the shells. In other words, one of the layers of clothing, okay? Losing an electron may leave the outer shell empty, which means it loses the outer shell, and so it makes the atom much smaller, okay? So here's a little visual, and basically gaining electrons does the opposite of all this, okay? Gaining an electron makes it bigger, okay? And so we have sodium. Sodium atoms are going to shrink in size when it becomes an ion, because it becomes positive, it loses an electron. So if it loses an electron, okay, think about what happens. If it loses an electron, it becomes more positive. If it becomes more positive, it's going to suck in the electrons more, okay? So that's why the sodium atom gets smaller. Let's look at chlorine. Chlorine becomes a chlorine minus. Chlorine becomes a chlorine minus, so it gains an electron, so it's going to get bigger. It gains an electron, so it's going to get bigger. Okay? All right, ionization energy. Ionization energy is the energy required to remove an electron from the gaseous atom. So ionization energy is the energy needed to make an ion. The energy needed to make an ion by removing the electron. Okay, ionization energy is taking the toy away from the kid. How much energy do you need to take the toy away from your little brother or sister? Okay, so the video showed this. Hydrogen has one electron, so taking the toy away from him, not that big a deal. But helium has a full shell, does not want to give it up. It is not going to give up that toy. Okay, it's not going to give up that electron. So the ionization energy is going to be extremely high. All the noble gases are extremely high. So we have helium, neon, argon, krypton, xenon. All of these ionization energies are going to be super high. Why? Because it does not want to give up an electron. Why? Because it's satisfied. It has a full valence shell. But lithium wants to give it up. Here, take my toy. I don't want it anymore. I'm sick of Thomas the Tank Engine. And then it goes up, and then it dips down a little bit, goes back up, dips down a little bit. Now, if you guys are curious about why it dips down, I'll explain it in more detail, after class, at the end of class, or during office hours. Okay, if you're curious about why it dips down, but that is more of a honors level type of thing. Okay. All right. So generally speaking, as you go left to right on a periodic table, it's easier to take an electron, so the ionization energy is, it's harder to take off an electron, so the ionization energy is higher, okay? Taking off an electron, easy, harder, 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 super hard, okay? All right, now the octet rule. What is the octet rule? We've been talking about, the video has been talking about, and I've been talking about a full valence shell. A full valence shell. The full valence shell is going to be your octet. Okay, every single atom, with the exception of the first period, every single atom wants 8 electrons in its valence shell. It wants 8. That's called the octet rule. Groups 1 and 2 will lose an electron or 2. Okay. Group 1 will lose 1 electron. Group 2 will lose 2 electrons, so that it can become like a noble gas. Okay. Easy to get rid of electrons. Low ionization energy. I explained that a little while ago. Group 6A and 7A. 7A is the halogens, right next to the noble gases. They are so close to being noble. They only need 1 more electron and they're noble. Okay, group 6A, they only need 2 more electrons and they're noble. And so group 7A, they'll gain 1 electron and they'll become a -1 charge. Group 6A will gain 2 electrons. They're only 2 steps away from the noble gas. So they'll gain 2 electrons to form a -2 charge. They do not want to lose any because they're almost there. So the ionization energy is going to be a lot higher. Okay, they don't want to lose any electrons. And high ionization energy. Okay, so here is the trend for the ionization energy. Generally increases as you move from left to right, and generally decreases as it goes from top to bottom. Okay, ionization energy increases as you go from left to right. So we talked about that, but why does it decrease? Why is ionization energy decreasing as you go from top to bottom? So I want you guys to think about this. Your little brother has a toy, and this toy, he only has 1 toy. Well, it's going to be hard to take that toy away from him. He's just going to hold on to that toy for dear life. Now, let's say this same little brother now, you move down the periodic table. Now you have all these toys, and they're scattered all over the room. Well, then it's going to be easier to take a toy away from him. Why? Because he has so many. So as you move down this periodic table, you have more and more electrons, a lot more electrons, and so taking an electron away is going to be super easy. Okay? All right, let's talk about electronegativity. Electronegativity is how attractive you are. Electronegativity is how attractive you are. So electronegativity is the ability to attract electrons. So electronegativity, so let's think about it. I want more electrons. Electrons, come to me, right? That's basically what electronegativity is. So it increases as you go from left to right. Let's think about that. Over here, do they want electrons? No, they want to give them away. So they're not going to want to attract electrons. Over here, do they want electrons? Yes. I want an electron. Okay. So they are highly electronegative. Now think about the noble gases. Do the noble gases want electrons? Nope. Does not want another electron. They're already happy the way they are. Okay. So they are going to not have any electronegativity. Okay. Notice this coloring here. We have electronegativity less than 1, between 1 and 2, between 2 and 3, between 3 and 4. This whole column right here, this whole group, it's white, which means it has no electronegativity, 0. Okay. The highest electronegativity, top right-hand corner, and it decreases as you move left, and it decreases as you move down. Okay. If you have a lot of toys, do you want more? Not as much as if you have fewer toys, right? So if you have a lot, if you have almost a whole set of, I don't know, Cars toys or Thomas the Tank Engine toys, whatever. If you have if the little toddler has all those toys, it's not going to need anymore. Okay, so over here, don't need much electrons. All right. All right, so here is a summary. So write this down. This is very important. Here's a summary. Atomic radius is, now it sounds like all this stuff that I just taught, it sounds like there's a whole lot of stuff to remember. There's only one thing you need to remember. This one thing right here. This one thing is the only thing you need to remember. Just remember everything else is opposite. Okay? So right here, atomic radius gets bigger as you move left, down. Atomic radius gets bigger as you move left, down. Left, down. Atomic radius gets bigger as you move left, down. Okay, the atomic radius increases as you move left, down. Mr. Cheng, you just said that. I know. Over and over again. It's called repetition. Atomic radius increases as you move left, down. That's all you have to memorize. Why? Because all the other trends, ionization energy, electron affinity, electronegativity, all the other trends are the opposite. Upright. It increases as you go upright. Okay, everything else is upright. Atomic radius is left down. Okay. Atomic radius increases as you move left down. All right, so here's another video. Let's take a look at this one.
Hello, I'm Hank Green. Welcome to Crash Course Chemistry. Last time we left off with Mendeleev believing he had discovered a cosmic mystic reality about the world, but in fact, he had discovered the effects of his worst enemy, tiny, invisible particles. Electrons, which are so marvelous and peculiar that it wasn't until 80 years after Mendeleev's first periodic table that they were really understood by anyone, and to this day, still very, very few people understand them. But in like 10 minutes from now, if all goes according to plan, you will be one of those people. So let's do this. In 1865, before Mendeleev published his first periodic table, a young chemist and activist, John Newlands, published a paper on the periodicity of elements, comparing their repetition, at least the first 2 rows of it, to a musical scale, all do, re, mi, fa, sol, la, ti, do and stuff. Maybe, he theorized, lithium was just sodium, but an octave higher. Maybe they were, in a sense, the same note. He delivered this idea to the Royal Academy, the most prestigious group of scientists in the world, and they basically laughed him off the stage. Music is art, and chemistry is science. Now, describing science in an artistic way might be a fine parlor trick for helping little babies or women understand the work you do, but they have no place in the Royal Academy. That's my impression. But there was no way, of course, of knowing that it turns out that John Newlands, when it came to the actual functional physical reality behind the periodicity of the elements, was more right than any of the scientists who laughed him off the stage that day. And I never got to find out how right he was. We didn't discover that his analogies were barely analogies until long after his death. But it turns out that reality is like a kind of music. And maybe you want to laugh me off the stage right now, but bear with me. Before quantum mechanics, scientists envisioned the atomic world as just a miniature macroscopic world. Electrons seemed to just be particles orbiting around a nucleus. In fact, there was a Great Dane, no, Nick, other kind of Dane, Niels Bohr, yes, like certain other people I might name who sometimes felt.
Okay, so I'm just gonna stop the video there. I do recommend you guys watch the rest of this video, but a lot of the stuff that I already covered is in this video. I just wanted to show you that Newlands, his idea of the octaves, okay, I talked about that before. It was laughed at, and he died thinking, you know, he died not knowing if he was completely correct or not. So I want to kind of let you guys know, when people are laughing at you or thinking that what are you thinking? Well, you might be right. They might be wrong, okay? So just a little booster there, okay? All right, so let's take a look at the section check. Which block spans 14 elemental groups? Which block has 14 elemental groups? Remember, groups are columns. So which block has 14 columns? Don't type it in yet. I mean, don't press enter yet. Okay, which block has 14 elemental groups or 14 columns? In 3, 2, 1, answer. Excellent. Okay. All right. It is the F block. Good job. All right, let's move on to the second question. The ionic radius of a negative ion becomes larger. Okay, ionic radius, in other words, the size, the ionic radius of a negative ion becomes larger when? Okay, when does it become larger? Moving up the group, moving right across the period, moving down a group, or the ion loses electrons. So think about that one. Think about your little brother losing a toy. What's he going to do with the rest of the toys? An ionic radius, the size, gets larger when? 3, 2, 1, answer. A lot slower on this response. Okay. All right, so I got a couple D's in there, so let me explain D. The ion loses electrons. What happens when it loses an electron? What happens when your little brother loses his toy, or somebody steals his toy? He's going to get the rest of his toys, and he's going to bring them closer to you. So the size decreases. If the electron is taken away, the atom becomes more positive, so it sucks the rest of the electrons in closer. Okay, so if it loses an electron, it's not going to become larger. C is the correct answer. Moving down the group. Now, let me give you guys a little legal way of cheating on a multiple choice test. Legal way of cheating. You see this says moves up a group. This one says moves down a group. Moving up a group, moving down a group. Yeah, it's gotta be one of those. You know something changes as you move up, and you know something changes as you move down. You just saw that in the video and in my lesson. It changes as it goes up or down. So it's going to be either A or C. Okay? So it's a 50-50 guess now. Moving down. Excellent. All right, so now I'm going to review a few things because in your homework assignment, I included stuff from 6.1. So I'm going to review some stuff from 6.1, okay? So take a look at this periodic table. As you go to the right, are you becoming more and more metallic or more and more non-metallic as you move to the right? Good, non-metallic. As you move to the left, are you becoming more metallic or more non-metallic? More metallic. Now take a look at this way too. If you're moving down, are you becoming more metallic or non-metallic? Okay, more metallic. As you move up, you're becoming more non-metallic. Okay, so here's the trend. As you move left and down, you're becoming more metallic. As you move right and up, you're becoming more non-metallic or less metallic. Make sense? Okay. More metallic, more non-metallic. All right. Now, let's talk about groups. I know I talked about groups a lot, but let's review it because you're going to need it for your homework assignment. Your homework assignment is worth 18 points. It's not the 10 points. It's more than that because we're covering 2 sections. All right, so it's going to be worth 18 points. Let's talk about the group. Group is a column. Column is a group. It's also called a family. Now, all the valence electrons in that one group will be the same. You're going to have the same number of valence electrons. You're also going to have similar physical properties. You're going to have similar chemical properties. Okay? So in that one group, there's going to be a lot of similarities. Valence electrons are the same. Similar physical and chemical properties. The group number, family, column, whatever you want to call it, is all the same. Okay? Very, very important. All right. So here are 4 slides that I showed you on Monday or Tuesday. I just took it straight from there. Okay. Again, you're going to need these to answer your questions on your homework assignment. So we have physical properties of metals: shiny, conducts heat and electricity, malleable, ductile, and almost always solid. The only one that's not solid, mercury. And mercury is, the chemical symbol is Hg. Hg. Okay. Next, nonmetals, basically the opposites of metals. The only one that's liquid at room temperature is bromine. So there are only 2 elements on the periodic table that are liquid: Hg, mercury, and Br, bromine. Those 2 are liquid. Everything else is going to be solid. Okay, why am I mentioning that? You're going to have some questions on it. Halogens. What do you know about halogens? They're right next to noble gases. They form diatomic molecules like F2, Cl2, Br2, and so on. And then we have noble gases. Noble gases are unreactive. They don't like to react because it has a full valence shell. And the noble gases are monatomic. It doesn't even like to react with itself. It just likes to be noble by itself. Okay? All right. So you guys are working on, it says work on 6.2, 6.3 homework assignments, but I clumped them into one. Okay, it's one big assignment. And it also includes a little bit of 6.1. So you have one homework assignment. It says chapter 6 on it. And your notes, all your notes. Chapter 2, section 2 was very, very small. You have 6.1, a little bit of 6.2, and 6.3, okay? So those notes and the homework assignment is due today. There is another assignment. It's called it's basically putting the electrons in order, okay? That's a 10-point assignment. It's a simulation. You basically put the elements into the periodic table, you do a screenshot of it and submit it, okay? Again, office hours every day at 1 to 2, but on Fridays, 11:30 to 12:30. Same Google Meet code, okay?